This is a vapor pressure question, and it tells you that the vapor pressure of solid iodomethane, here's the formula for that, is 157.37 millimeters of mercury at 2 degrees Celsius. And we're going to put a 0.6 gram sample in a vessel, and really our process is going to look something like this. I like to draw it in an Erlenmeyer flask. So we've got a some sort of container, and it's got a volume of 379 milliliters, and we'll just include everything up to the corked area, the rubber stopper. And then inside there's a little lump, and it's 0.6 grams of iodomethane. And the question is, so how much of the iodomethane vaporizes? How much of the iodomethane, which I guess it doesn't say this, must be a liquid. No, it's solid. Yeah, solid. Vaporizes. Well, maybe the process is actually subliming, but it is still considered the vapor pressure. Solid going to CH3I gas. And our thought is, let's calculate if all of it goes from solid to gas, goes into the vapor phase, and we'll get a pressure from that. And if that pressure is greater than the vapor pressure, then not all of it vaporizes, because the maximum amount that will vaporize is to create this pressure. And if it gets to this pressure, it will establish an equilibrium. So some will vaporize, and some will, let's say some will sublime, and some will deposit. Deposition is the gas to solid phase. And that's what this question is about, is how much can vaporize, or assume all of it vaporizes and see if it can, and it will all vaporize or sublime if the vapor pressure is less, or the pressure is less than the vapor pressure. Well, if that made any sense, let's go ahead and continue and see if we can figure this out. So we know we have the grams, and we can calculate moles. And what we're going to do is figure out how many moles we have. We have our volume, we have our temperature. We'll figure out our partial pressure. Now, to do that, we need moles. Moles is going to be the 0.6 grams. We have our molar mass, 141.9. .6 divided by 141.9, we get 0.00423. That's going to be our moles. We know R, we know T. Well, T is 2, plus 273 is going to be 275. Let's see, we don't know our pressure. It's going to be equal nRT over V, where I'm going to convert this into liters. So away we go. My R value for ideal gas is 0.08206. With liters, atmospheres, and moles in Kelvin. So this answer is going to be actually in atmospheres. That's key, because our vapor pressure has been given in millimeters of mercury. So let's see here, 0.00423. times 0.08206 times 275 divided by 0.379. I get 0.252. As the partial pressure of iodomethane if it all goes into the gas phase. Now I'm going to convert this into millimeters of mercury. And I'm going to use my 0.252 times 760. I get 191.5 millimeters of mercury. Okay, so if all of it went into the gas phase, this would be the pressure. The vapor pressure sets the limit on how much the pressure can be in this vessel. So it hits that pressure before it gets to all evaporate, to all go into the gas phase. So now, at equilibrium, what will be the pressure in the container? It will be the vapor pressure because it cannot go any higher than that. So 157.37 will be the partial pressure of iodomethane because no more, that's the highest pressure you can get. That's what the vapor pressure is. And it just means this will be the partial pressure, and I should put units there. And the other thing we can say is not all of the iodomethane will go into the gas phase. Will be gas. Some of it will still be solid, and that solid and the gas will be in equilibrium.